In this video, I will provide an introduction into the experimental measurement programs, how they work, what files they record, and what are the conventional naming rules, and how these files can be processed using own developed program, as well as in the future presentations using Origin or Igor Pro. On the top image here, there is a schematic of a typical pump probe experiment, and on the bottom there is an example of a transient signal. It is basically the signals that we record. In this case, is voltage from the photodetector, and specifically in this case, we have three different control variables. The first one is the most obvious, is the time delay of a translational stage. We can move retroreflector on the translational stage, increasing the time delay between probe and pump, and hence we have the dependence versus time. Another two control variables are the temperature, controlled by the temperature controller of the cryostat, and the pump power. Pump power is the least obvious here, but if shortly, we can rotate the half-wave length plate, and together with the gland polarizer after it, we can control the pump intensity, the pump power. Here on this image, what is important detail, how the program works. The program that is written in C#, it is two-threaded, meaning that it's not just make a steps, record points, and makes another step. It moves continuously and it records points continuously. And it adds two effects. First is that while recording, each recorded data point, it will be recorded at a random position. We cannot predict it before recording position. And secondly, the recording speed of the data points are limited by the repetition rate of the laser, which is 1000 in our main system. The limit of the position recording is limited by the velocity of communication with the translation stage, which is much less. It's around 30. In this, because of that, we record much more pulses than we record position. So the first algorithm that we do in the program is that we use linear interpolation for the data, meaning that per every recorded pulse, we assign it a unique position, assuming that, as you can see from this graph, that the assumption can be done that our translational stage moves with the same velocity. It moves with a constant velocity. And that's how we get our transient signal. Another thing that we do is, instead of just running one scan, we record the same parameter of scan, either the same temperature or the same power, several times, and then we average. As you can see from the left, the signal to noise is much worse, and there are some different peaks. But if you look at the right, our signal to noise is much better. And that is called multiscan. And because of these two things, because we make linear interpolation and then we average over a few scans, the program saves three different types of files. So here I have some of the examples of those files that I can quickly show. The most important file that we will be looking into is average ROT. So the files, as you can see in the presentation, the only difference is the end of the file, or I will call it a suffix, which is the end part of the file. The average ROT is the file where you can find this average scan. Let's, for example, for this data set, I have polarization dependent measurements. I have two channels. and those are average scans. But if I open, let's say, data or raw data, let's open raw data. In the raw data, I have firstly IROTEC columns that recorded, then interpolated, and then 2 channels. Note that IROTEC I record only for one. Interpolation works pretty reliably, so I don't have to record here IROTEC initial, but one for the testing purposes. It was there for the testing purposes, and it's still there in case of some bugs in the program that we try to clean when we find it. And then you see all of the different individual scans with 2 channel signals and then reference. 2 channel signals. So here, in this case, it's the reference because it's not. The reference is actually 2 channel measurements, which is this program was updated from the previous version where there was 1 channel measurement. So even though raw data names is reference channel, in reality is 2 channels, and everything here is 2 channels. So the context of the file depends on the measurement here. And here you can see all of them, and also you can see that there are some 0 values after. It's also specifically to this program that program allocates more points, and all the 0 points, they will be cleaned. And here you have the data file, not raw data but just data file. And in the data file you have already cleaned data, but still not average. You see that there is no extra zeros, there is 2 channels, and then you have average rot, which is the main file that we will be using in most of the program. The next thing is important to define 2 different measurement modes. One is power dependent measurement, is in which we change the rotation of the half wavelength plate, and within each rotation we do multi-scan. We do n scans, and then we get one average rot 0 file, for example. Then the next rotation average rot 1 and average rot n. Here is a mistake, it should be m. And then for temperature dependent measurement, we do not change rotations. For classic temperature dependent measurements, we record at 1 rotation, we record all temperatures. The new version of program allows to do simultaneously power and temperature dependent measurement. However, in the end, the data still will be processed as 2-dimensional data, either with the respect of temperature or with the respect of power. So in the variant, you will have the same rotation and different temperature, or the same temperature and different rotations. And this is important to distinguish because, for example, for temperature-dependent measurement, usually the temperature naming is inside of the file. For example, here you have V305, temperature-dependent. Here is 63 milliwatts, 50 picosecond, 3 to 250 kelvins. This is all prefix. This is information about the scan. Then it's 30. 30 is the key number here. 30 here stands for 3.0 Kelvin, or for 3 kelvins. This is exactly what the program, the analysis program, for example, pneumaticity or text shuffle will need to get that file. So let's look here, for example. I have those files. So as you can see, here I have 30, then 150, 270. These are the counter. The different number corresponds to different temperature. And finally, we have suffix. Suffix is everything else. In the program, as we will see in the another videos, you will have to define prefix in one text box. Number you have to define by text boxes separately. Program will calculate this number separately, and then you have to define suffix. For power-dependent measurement, however, you do not have suffix. And the reason for that is because the rotation counter is exactly on the end of the file. So if you compare it with the temperature-dependent measurement, you see that rotation is fixed. The counting goes inside of the file name with some variable. For the power-dependent measurement, the counting goes in the last number. And finally, when you work with the data, preliminary analysis that is explained in the presentation 2 and 3 will show how to make initial processing of the bare voltage signal into transient reflectivity, for example, delta R by R, to subtract zero value, to divide by zero value, and to also put the time delay zero in the correct position.